Hi everyone, welcome back to Chem Help ASAP. Today we are going to be talking about photoelectron spectroscopy. Now this type of spectroscopy is related to the photoelectric effect, and we use it to determine the binding energy of electrons and also the relative number of electrons at different energy levels. We can also use a spectrum to determine an unknown element. Let's see how this works. The best place to start when talking about photoelectron spectroscopy is, of course, the definition of photoelectron spectroscopy. So, in photoelectron spectroscopy, we are measuring and charting the ionization energy for all electrons in an atom. Remember, ionization energy is the energy to remove an electron from an atom. Now here is an example of a photoelectron spectrum. We will talk about this in detail. So photoelectron spectroscopy is related to the photoelectric effect. So when atoms are exposed to any kind of electromagnetic radiation, as long as it is greater than the threshold frequency, then that substance will emit electrons. This energy is the ionization energy. You'll also see it called the binding energy of that particular electron. But atoms generally have multiple electrons. So electrons that are farthest from the nucleus are going to require less energy to eject than electrons that are closer to the nucleus. So remember, you have an attraction between the electrons and the nucleus. The more the electrons feel that attraction, the more difficult it is going to be to remove them from the atom. Now, energy is always conserved. So the energy of the electromagnetic radiation that you are bombarding the atoms with is going to be equal to the binding energy of the electron. Remember, this is also called the ionization energy, plus the kinetic energy that the electron has as it's ejected. So here is an equation that we can use to equate these quantities. Again, the energy of the electromagnetic radiation is going to equal to the binding energy plus the kinetic energy. What this means is that when you have electrons with a low binding energy, meaning they are very easy to remove from the atom, they are going to be ejected with a higher kinetic energy and thus have a higher velocity. So remember your formula for kinetic energy. Here it is right here. It's 1/2 mv squared. Remember, v here is velocity. So when your binding energy is low, your kinetic energy is going to be greater. So thinking about this physically, you have electromagnetic radiation hitting a substance here. This is a bulk substance of an element. What happens is you're going to get electrons being ejected. These electrons are going to have various kinetic energies, and they're going to correspond to various binding energies. So let's see what happens when we take a look at what the binding energy is and how many electrons are ejected. This is where we get our spectrum. So our peaks in our photoelectron spectrum, which is also called a PES, are going to show the binding energy. Again, it's the same thing as ionization energy of the electron. This is on the x-axis. So you can see right here, this is binding energy. On the y-axis are the relative number of electrons. Again, you can see it's labeled right here. Going back to the x-axis, notice that the binding energy decreases from left to right. So these electrons down here are the easiest to remove from the atom, which means they are farthest from the nucleus. Now, conversely, the electrons with the highest binding energy over here are going to be closest to the nucleus. These took a lot of energy to remove from the atom. So what this does in the order of the peaks is it means that your peaks are arranged according to the subshell energies. So these are arranged according to 1s, 2s, 2p, etc. So we can identify these as 1s, 2s, 2p electrons. What also helps is you can look at the height of the peaks, and that is going to correspond to the relative number of electrons. So peaks with the same height have the same number of electrons. So if I label this peak as my 1s orbital and this one as my 2s, then yes, of course they are the same height because they have the same number of electrons. Now check out this big peak that's next. This is my 2p peak, and you can see that it is about 3 times the height of my 2s peak. So if I continue to label my peaks, This is my 3s peak, and this is my 3p peak. Now let's talk about how many electrons we have so we can identify this atom. So we know the first peaks are going to be full, meaning the 1s peak is going to have 2 electrons, the same as the 2s peak. My 2p subshell is also full. That means it has 6 electrons. Again, if I look at my 3s peak, you can see it's the same height as my 1s and my 2s peaks. So it also has 2 electrons. But now it's interesting, so check out the 3p peak. It definitely does not have 6 electrons. It is not as high as the 2p peak. It is about twice as high as the 3s peak, meaning it has twice as many electrons. So there are 4 electrons in the 3p orbital, meaning that this atom is sulfur. So if you are given the PES of an atom, you can identify which atom it is based on the number of electrons and which orbitals those electrons reside. In my mind, I'm using the PES to identify the electron configuration, which then helps me identify the atom. The most important thing to remember is your x-axis runs from higher binding energy to lower binding energy. Now we are very used to the x-axis running from lowest to highest, so make sure you read those axes very carefully when looking at a PES. I hope you found this video helpful, and thanks so much for watching.